This is Chapter 8, Section 1, and we'll be looking at integrating using basic integration rules. This section starts on page 516, and on that page in the margin there is a list of integration rules that we'll be using. Many of these are probably in your reference booklet, but for this particular lesson it might be a little easier to use the ones that are listed on this page rather than search through the many that you've got in your booklet. Okay, we're going to start today looking at three integrals that are a little bit different but look very similar. And here they are. Okay, you might notice that all three of these integrals have the same denominator. They all have a 4 in the numerator, but the only thing that's different is that this one has x and this one has x squared. And that might seem like a simple little difference, but it completely changes our approach for these integrals. So let's look at the first one. In this first one, since the 4 is a constant, I can take it out. Okay, and now I'm going to use the arctangent rule, which on this page is number 19. Okay, so this is our arctangent rule. And in this example, we can see that we're going to let u equal x, and a will be 3 since I've got a 9 there. So this is going to give me 4 times 1/3 arctangent x over 3 plus a constant. Okay, and if we clean that up a little bit, I'll get 4/3 arctangent x over 3 plus c. So that's what we can do with this expression if I have a constant in the numerator. Let's take a look now at the second expression. I have a 4 in the numerator again, but this time I also have an x in the numerator, so I'm going to have to do something a little bit different. In this case, I'm going to use what we call the log rule, which looks like this. when I look at this one, I can see that the derivative of x squared is going to be 2x. I've got 4x up there, so I'm going to take a 2 out. So that now I have 2x over x squared plus 9. I'm going to let u equal that x squared plus 9. And then the 2x will be du. So this is now 2 times the integral of du over u. And equation 5 tells us that this is now natural log of the absolute value of u plus a constant. So really a completely different approach for this one than we had for this one. Okay, in our third expression, we have the same power of x in the numerator and the denominator. So we need to go ahead and do that long division and break this up into two integrals. So I have x squared plus 9, and here I have 4x squared. We know that x squared goes into 4x squared just 4 times. And then our remainder is going to be negative 36 over x squared plus 9. This is our remainder. Okay, so now I'm going to break this up into 2 pieces. Okay, the 4dx is just going to give me 4x. I'm going to bring this 36 out. And then apply that arctangent rule again, same rule that I applied up here, which is going to give me 1/3 arctangent x over 3 plus c. Okay, and I can clean that up a little bit. So I have 4x minus 12 arctan, not actan. Okay, and there you have it. And if you're wondering at this point, well, how do I know what rule to use? How am I ever going to figure that out? The answer is practice and experience. The more of these you do, the more familiar you will be with the different forms, and you should eventually get to the point where you can look at something and say, okay, I need to use the log rule on that. I need to use the arctangent rule on that. But the only way to get there is to practice doing them. Okay, let's move on. Okay, in this integral, I've got a square root in the denominator, and I've got a numerator that's just a linear factor. What I can do with this numerator is split it and make two integrals. So that's going to look like this. The first one will be just x over this denominator. And then the second one will be 3 over the same denominator. Okay, so now I have two separate integrals that I can work with. For this first integral, I need to have 2x up here instead of just x. And I need it to be negative since my rational exponent for this would be negative. So I'm going to put a negative 1/2 on the outside of the integral, which allows me to put negative 2x on the inside, and then I'm going to rewrite this with a rational exponent of negative 1/2 dx. When I integrate this part, now I'm going to take a look at this part. I've got that 3 on the top by itself, so I can just bring that out. And then I'm going to rewrite this just a little bit and change that 4 to a 2 squared minus x squared. And there's my dx. Okay. Now I can integrate each piece separately. I end up with negative 4 minus x squared to the positive 1/2 power plus 3 arc sine x over 2 evaluated from 0 to 1. Okay. And that arc sine rule we hadn't used before, but this is rule number 18 on page 516. Okay, now we evaluate at 1 and 0. So I'm going to get negative square root of 3 plus pi over 2 minus 2 plus 0, minus negative 2 plus 0. And if I want a decimal approximation for that, it's approximately 1.839. Okay, so this is an integration where we use the arc sine rule. In our next example, we're going to use the substitution a squared minus u squared to work this problem. This is the problem. Okay, integral of x squared over square root of 16 minus x to the 6th power dx. So to substitute for this expression, a is going to equal 4, and u is going to equal x to the 3rd power. And if u is x to the 3rd, then of course du is 3x squared dx. Okay, so now I know I want 3x squared on the top. So I'm going to put a 1/3 out in front. That allows me to put 3x squared up here over the square root of 16 minus x cubed squared dx. Okay, now this 3x squared is my du. So I can write 1/3 du over square root of 4 squared minus u squared. And now I'm going to use the arc sine rule again, which is number 18. Okay, and now that I have this worked out, I'm going to reverse my u substitution. Replace the u with x cubed. And I'm done. In our next example, we're going to take a look at this integral. Okay, at first glance, this doesn't appear to match any of the rules that we were given for this section. But we're going to use a little trick here. We're going to add e to the x power and then subtract e to the x power from the numerator. Okay, you know you can add and subtract the same thing without changing the value. Okay, now I'm going to split this up into two integrals. Okay, and this first integral, of course, this is just 1. So the integral of 1 is just going to give me x. And now I can look at the second integral. I'm actually going to subtract, just take this negative out here, and get natural log of 1 plus e to the x plus c. Okay, and I used equation number 5 on this one. Okay, and just a reminder, I can split numerators. I cannot split this denominator. So what did I do? I made the numerator such that I could split it and give me the two integrals. Okay, so always remember that. I can only split numerators this way. Okay, here's another interesting integral. This one has sine functions, or not sine functions, but trig functions in it. As well as a natural log. Okay, and again, the approach is not real obvious here, but what I can do is look at doing a u substitution, and my two choices were either u is equal to cotangent of x or u is equal to natural log of sine x. And looking at those two possibilities, if I chose u equals cotangent x, then I have a little difficulty with du. But if I choose this one, u equals natural log sine of x, then du will equal and of course, sine of x over cosine of x is cotangent x. So this is the one that's going to work for us. Okay, we don't want to use that. So we're going to make this the integral of u du, where u is the natural log of the sine of x. Okay, and of course the integral of u is going to be u squared over 2 plus the constant. And now we substitute back. I'm going to bring that 2 out here. Plus our constant. Okay, if you want to check your work, you could take the derivative of this and make sure that you end up with what you started with. Our last example for this section is another trig function. Integral of tangent squared 2x dx. If you look at your list of rules, tangent squared x is not in the list, but secant squared x is. So we can use a trig identity to rewrite this. And here's a trig identity. Tangent squared u is equal to secant squared u minus 1. So if we let u equal 2x, then du would be just 2 dx. Then du would be 2 dx. So let's rewrite this. I'm going to need a 2 inside, so I'm going to put a 1/2 on the outside. And now I'm going to break this up into two integrals. 1/2 integral of secant squared u du minus 1/2 the integral of 1 du. Okay, this one's going to integrate to 1/2 tangent of u, and then the second one's just going to be u over 2 plus a constant. Now we need to go back and reverse our substitution, which is going to give us 1/2 tangent 2x minus 2x over 2 is just going to give us x plus the constant. Okay, so use those basic integration rules. Get familiar with them. The more you practice, the easier it will get. On page 519 in your textbook, there's a list of different procedures that you might use to make an integral fit into one of those integration rules. So that's a useful resource for you as well.